Today's video will be all about transfer learning in PyTorch. So we'll be looking at a dataset that you can find on pytorch.org. There's also a link in the video description. And my main contribution will be to give you some intuition, to give you some code explanation, and hopefully afterwards you'll be able to implement it on your own with your own dataset. And let's dive right in. How does transfer learning work? So transfer learning, the idea is that you train a convolutional neural network, could be any architecture, for example, a ResNet or a VGGNet, and you train it on a large data set like ImageNet. So in ImageNet, you have over 1 million images with 1,000 categories. And the network learns some useful representations, some useful features that you can use for your own task. There are two main ways how transfer learning is done. I will give you an example. So there you have an image, you feed it into a ResNet, and at every step of the ResNet you have a reduction in image dimension and an increase in channels. And you end up towards the end with 512 channels, for example, and a 7x7 image dimension. And then you do global average pooling, which leaves you with 512 channels, and you have one value for each of these channels. So you have the 7x7 dimension, you just reduce that to one value. So each of these channels has now learned some useful representation. So what you do is you flatten the whole thing out, and then you have a fully connected layer that predicts, like in our example, like we discussed earlier, for ImageNet, it predicts 1,000 categories. Now instead of 1,000 categories, we might only have 2 categories, and therefore we can remove this in the end and replace it with just 2 categories. And this is our new classification task. So what happens is we just continue training the network, and we backpropagate all of the error through the network, and we adapt our weights such that we can make a classification. And this is called fine tuning. So we use an existing network and we adapt its weights such that we can predict our new class. Then there is another way we can do, and that's called feature extraction. So the feature extraction approach is similar but different. So we can say that this, if ResNet outputs 512 channels and a 7x7 image dimension, we can say that this is our image representation. So these are the features that the network has learned for a specific image. And after the global average pooling, we have our features here. We flatten the whole thing. And then this is now our image representation. So we can do the same thing. So we have our 2 classes here. This is just the same. But the difference now is that we train a fully connected layer on top, and we have our classification here. But we don't adapt the weights, so we don't backpropagate the error back through the network. But instead, we only train on top of the network. So we have our representation, and we train a fully connected layer on top. But there is no backpropagation. So the weights, they will be frozen, they will stay the same, but just these weights in the fully connected layer at the end, these are the ones that we continue training until we have reached our a good validation accuracy. As described in the tutorial, we have fine-tuning, which is just initializing the network with a pre-trained network, and then we train on our data set. And then the feature extractor is that we get the image representation, it gets output, and we can now train something on top. So this would be the fully connected layer that we replace, and the weights in the fully connected layer are the ones that are trained, but the network stays the same. Let's now have a quick look at the data set. So our task is to classify ants and bees. We have 120 images each and 75 validation images. So it's quite a small data set, but since we're using the pre-trained network, it already has learned some useful features, and this will make it perform much better than just training on these 120 images. So you can just go over here, download the dataset and extract it. The dataset looks like this. You have a training and validation data, and already opened two, so you can have a look. So we have ants and bees. So here is an example for or an image for ants and an image for bees, and this is what we're going to work with. So from here, let's head over to the Jupyter Notebook and have a look at the code. I'll be using Jupyter Notebook. If you don't have access to Jupyter or you don't have it set up, you just head over to Google Colab, and you can even get a GPU or TPU for free, and you don't have to run it on your CPU, which might last much longer. You can go on the tutorial page and just directly run it in Colab from here, or you download the notebook and import it to your Jupyter environment. So I'll just run the first few lines, first few cells, the imports, and now let's have a look at how the data is loaded. Data transforms are here. You can see training and validation. So you have two pipelines where you put the data through and it gets manipulated sequentially. So here you have two ways of augmenting your data set. Here's an example. You have an image of a cat, and then with the first transforms you get a random crop. That means you crop somewhere here. So you have a crop with 224, 224, 224, 224, and another crop here. So this is the same, and it's still a cat picture. So you get two instances of from one image, from one example. So these images that you get from here are now you have now created new data that is still showing a cat. And the same goes for random horizontal flip, which just means that if you flip this image around, you still have a cat image, right? So if you flip these ones, they still show the same content, just horizontally flipped. So you also get more data that you can use to train your model with. Now, after we have the augmentation done, there is a 2-tensor, so we just transform the images to tensor format, so PyTorch can read it. Here we have a normalization going on with the ImageNet stats. Actually, you don't need to normalize it with your own dataset stats. It will just make the training, will improve the training. You can try it out, just uncomment this line and uncomment this line. See if there are any changes. It should make the model perform better. So that's what you usually do. You normalize it. So here's the mean, here's the standard deviation, and you have the 3 channels, red, green, and blue, and you normalize it with with these stats that were calculated on ImageNet, because that's the original data set that the model was trained on. So that's what you usually do, but you can still play around and see if it actually makes a difference. The validation pipeline looks similar. There is no augmentation, of course, because we just want the actual image. So we just resize it to 256, and then we do a center crop with 224 pixels. So you just get the actual object that you want to classify. It would be possible to do augmentation, but that's maybe not what you want, because in the end you want to classify your images and you don't want to create instances again and then use them as like for testing your model. So you just do a center crop and then feed the image in where you have most of the image content, and then you have a 2 tensor again, so the PyTorch readable format, and the normalizations that are going on. I'll just run this one, this cell, and then here you have the data directory. Here we load the image data, so you have your trained images, your validation images, and you just pass in the path and the transforms for each of these. You create a dictionary. It just looks like this for validation. You have the exact same transforms as above, and like you get some information where the location is of the data, how many data points you have. Same goes for training data. So here you can see there are 244 data points in the training data, and here's the location. And of course the transforms are exactly the same as above. Now we have the image data sets, so we can set up the data loaders. You have one for training, one for validation. Here you pass in the image data sets, and you have a batch size of 4, which is totally fine since it's a small data set. So the data loader is just sampling images, and you turn shuffle on. Usually you turn it on because you want it to shuffle it at every epoch, so it doesn't just learn the same pattern or like the same sequence of data over again. So this will make the model more robust. And you have numWorkers 4, which is the number of sub-processes that are running, and this will speed up the data loader. So this will just speed up the training process later on. We will need the dataset sizes for calculating the loss and the accuracy when we're training. So you can just see, and we've seen that already, this is how many training and validation images we have, and the class names are ants and bees. So you have category 0 ants and category 1 bees. You can specify what device you want to use for training. So usually you want to use the GPU or a GPU if you have one. If you don't have a GPU, you can still head over to Colab and just run it, since it's gonna speed up the training. If you run it on your CPU, it will take much longer. So you can run the cell, and then if you have CUDA, that means you're using a GPU. This function lets us visualize some images. So you load the image, and then you can see here that you multiply the image input by the standard deviation, and then you add the mean to it. So remember, we had the normalization step. To revert the images back to normal, we need to do this. Otherwise, we would get the color channels all messed up. And then here's clipping. So if there is a value that is below 0 or above 1, we just clip them to 0 or 1. So let me just run this, and then you can see here one batch of the data loader for the training data. So you can see you get a batch size of 4, and then you have 3 color channels, 224 by 224 images. And let's just visualize it with this function, and you can now see here some training images. So the first three ones are bees, and then you have an instance of ants. So we had 1 for bees, 0 for ants. If you just run this again, so the data loader is just sampling some data from the training data. So you run it again, you get a different batch of data. So this is, just repeat this. So now you see 3 ants or training images of ants, and you get 1 training image for bees. So let's head over to the training now. We want to keep track of time, obviously, so we can estimate how long it takes to train the model. Also, we want to keep the best model at every epoch. So we just initialize this here. This is how you do it. So model.state underscore tick is how you get the model's weights and the entirety of the model. So here we just initialize it, and later on you, at every epoch, you check the accuracy and see if it's a new highest accuracy, and if it is so, you just overwrite the best model. So let's now have a look at the training loop. Prints the current epoch we're in. Here you can see we set the model to model.train or model eval, depending on what mode we're in. So it's important because ResNet has some layers like batch normalization, where you get different behaviors depending on whether you're in training or evaluation. So you don't need to know batch normalization. You can look it up. There are lots of resources, but you just have to know that it's important to set model to model.train or model eval such that the model behaves exactly like you want it to. We initialize the loss to 0 and the number of correct classifications, and then we load the data with our data loaders. So we do that for train first and later for validation. And here you can see we have to copy the labels and inputs to our GPU. That wouldn't be necessary if we were training on a CPU. Since we're training on a GPU, we have to make sure that the data and labels, they all sit on the same device. We set the gradients to 0, and this is, you should never forget to do this, because if you forget to include this line, it will just accumulate the gradients and the backpropagation might not work as you expect it to work. So when we're in the training phase, we get our outputs and then the predictions. So now we have a criterion. In this example, this is cross entropy loss, where we compare our outputs, what we predicted, and labels, correct labels. And if that's the case, so if we're in the training loop, we're doing a backward step, so that you have loss.backward, and then you do the backpropagation step with your optimizer. Here you can see that we have the running loss, and we actually multiply the loss times 4, which is our batch size. So this is because the loss that you get, it's already the average of the current batch. So you just multiply times 4, so you get the original loss, and then for the corrects we just check if the predictions and labels, if they're the same, and if not, we don't add them. Otherwise we'll just add new ones. So here you have another thing that is a scheduler, and you might ask now, what is a scheduler? And you can't see it from just this function, but if we have a look down here, there is this scheduler. So this is actually changing the learning rate that we have in the model. So every 7 epochs, the scheduler, it just decays the learning rate by 0.1. So this is just something we do in the training to make the model converge faster. At the end of every epoch, we print the loss and the accuracy, so you can see this is calculated here, and then you check if you get a new best accuracy, and if so, you replace the model, you override it with the new best model. And so the main difference between the training and the validation is that you have here phase equals train. So for train, this is true. If it's not true, then we won't calculate the gradients, because this is set gradient enabled is false, and you also don't have this step, which is the backward step. So you will only calculate the prediction accuracy and the loss, and then print it out, and then keep track of the best model. To visualize what the model has learned after training, we have this function, and it basically just prints a few instances of validation pictures and shows us what prediction the model has made. So this will be useful for evaluating how well our model performs. To actually fine-tune on our data set, we use a model which is called ResNet 18. You set pre-trained equals true. That means you take the pre-trained model, so you don't take just the architecture and you train it from scratch, but you already take the pre-trained architecture that was trained on ImageNet, and then you have the number of features in your fully connected. So if I run this, you can see that number of features is 512, just like I showed you earlier. The interesting part here now is that we have the model's fully connected layer, and we map from 512 features to 2 categories, so that's ants and bees. That pretty much replaces what used to be the architecture before. So if we have a look at the architecture, let's just plug this in, and then I'll just add, I'll just print it like this. So you can see here, this is our basic architecture. So you have the average pooling that I mentioned, adaptive average pooling to the, and then you have 512 features, and then you output 1000 features, and that's for the 1000 categories in ImageNet. But now this is what we're replacing here. So this is what you swap, and then how we continue to train the model. Just as we did in the training loop, we copy the model to our GPU. So we have the model and the data on our GPU on the same device. And here you can see the cross entropy loss again that we pass in to the train model function. And we use, as the optimizer, we use stochastic gradient descent. So we pass in the parameters, the learning rate, and we use momentum. So if you're not all too familiar with these concepts, it's not that important, but as I said, there are lots of videos that you can watch that can explain how they work, give you an intuition. In the end, they have all shown to work pretty well, and they make your model converge faster or improve your accuracy. So you can play around, replace some values or remove them entirely, and see if that really is the case. Yeah, let's go down and start training the model. So here we can see the author actually writes that it might take up to 25 minutes if you train it on a CPU. If you now have a GPU, it will take less than a minute. So we can see that every epoch actually trains quite fast. So let me just stop the video and then run it afterwards. The model has finished training and it took less than a minute. You can see the best validation accuracy is 0.93, and if we can just check where exactly this is the case, so we can see that at the 15th epoch we had our best results, and we can already see that the results were pretty good just when we started training. So the first validation accuracy in the after the first epoch was already 0.92. So you see that you don't need to train, you might not even need to train a long time to get good results. But so here we get a more stable validation accuracy at around 0.9. So let's just visualize some of the results. As we can see, we get some, like we see in the validation accuracy, the results are pretty promising. So to me, this looks all correct. We have some B's, and we can like run this again and just see if there are some cases where the model still confuses things. But to me, it already looks pretty good. So now let's look at the second step, using a ConvNet as a feature extractor. The only thing we have to change now is that we want to freeze the weights. So now what we're doing is we step through the model and then we set param required grad to false. So this means that you won't be able to backpropagate now. You won't be able to calculate the gradient and then backpropagate back through the network. So they will stay the same. But as we can see here, we still have our fully connected layer in the end. So we just train this part of the model and leave the base model as it is. Let me just run this and we can see how it performs. One interesting aspect of training this on a CPU is that this won't take as much time as for the fine-tuning. So feature extraction is way faster. You only have to compute the forward pass, and then you don't have the backward step. So the backward step is not necessary. You don't have to change all the weights in the ResNet. However, you have to still tune the weights in the last layer, in the fully connected layer. So it's an increase in speed, and if you don't have a GPU, you can try to run this and it will maybe take 5 to 10 minutes. So let's now compare the results, and we can see that it actually performs better than the fine-tuning. And that might be the case because the data set is quite small. So for small data sets, you might want to prefer the feature extraction. And if you have more training data, let's say you have 1 to 5,000 images, you could try using fine-tuning, and you might get better results than with the feature extraction. And here you can see some results. I'll just rerun this and let's check. This looks good. This looks great. So we have all correct predictions here, and that's about it. I hope you liked the video and I could give you some intuition of how transfer learning works. Here you can find another tutorial that's tackling transfer learning, and there are tons of tutorials on PyTorch.org, so feel free to check that out as well. Please let me know if you're interested in some other topics. I might include them in my future videos. Also, if you have any questions, feel free to ask.